Welcome to Hot Chips 28. Session 1. GPUs and HPC processors.
This year, we've worked hard to improve the attendee experience. We have upgraded the projection to full HD quality, so that's why all of the slides will be in 16:9 format, and we increased the size of the screen. All the presentations will be recorded, and the videos in full HD quality will be posted on our website after the conference. They will be password protected for attendees only until the end of the year, and they will be open to everybody after that. The Hot Chips presentations for previous years are always available on our website at the hotchips.org in the Archives tab. We worked with IEEE to make all the presentations back to 2005 available in IEEE Explorer as well. Some people prefer to search them in IEEE Explorer. This year's presentations are available for download. It's a different website. You should see that in the slides that are shown in the breaks, and they will be posted on the archives once the conference concludes. Like in previous years, we are providing internet access throughout the Flint Center. All the meals, snacks, coffee, and we have 2 receptions, one last night and one tonight. They're all included. And we have kept the registration fees flat in spite of the rising costs. This is the schedule of the conference. We have 2 sessions this morning. We'll have a relatively late lunch, followed by a keynote from Microsoft, then 2 more sessions in the afternoon, and the reception this evening. Tomorrow, we start earlier. We have 2 sessions in the morning. We have lunch, and then we have a keynote from Google, and 3 more sessions in the afternoon. So tomorrow will be a really long day. I hope you will find it very interesting. A quick note about parking. You must display a parking pass that looks like this on your dashboard. If you don't have one, you can get one from the registration. You should park in lots A or B, and do not park in spots that are marked staff or 30 minutes only. Even if you have the pass, those spots will get you a parking ticket. And we need your feedback, so please get one of these forms from the registration, fill it up, drop it back at the registration desk. Please let us know how we can improve the conference for you next year. And now I would like to invite to the stage the program committee chairs, Brian Chin and Subhashish Mitra, to give you a quick overview of the technical program. Thank you, and enjoy the conference.
Good morning. It's great to see everybody here. Subhashish and I are really honored to represent the program committee, who these people on the screen here have just worked tirelessly for the past 8 months to put the program together. And I know I'm biased, but I think they did a fantastic job, and hopefully you'll agree. But if you see us out in the breaks, we'd love to hear your feedback. Come approach us. We'd love to talk to you about the conference and things you liked or didn't like. Just some notes about the conference. Stefan showed you the schedule. This is our 28th year doing this conference, and it's really changed over time, and I think it's interesting just to look at how it's changed. So no longer is it just a Silicon Valley kind of Stanford Bay Area-centric conference. 38% of our papers and posters this year are from outside North America. And traditionally, this conference has been a microprocessor kind of conference. And our topic diversity is quite amazing this year. Of course, we have microprocessor papers, but we also have an architecture disclosure. We're going to have some GPU and HPC accelerator talks, machine vision, chips, interconnects, some really interesting chips for embedded, including some very novel sensing technologies, machine learning, big data accelerators, and of course, we've already mentioned a really interesting keynote about mixed reality from Microsoft, and then a topic that's certainly been in the news about autonomous vehicles from one of the pioneers in that field from Google. And one quick reminder, we have 14 fantastic posters that are out on the patio, and I encourage you to go out and visit with the sponsors and the posters during the breaks and the lunchtime. And so with that, I guess we're ready to begin. So in the spirit of the Rio Olympics, let the games begin. And I'll bring out Samir now to start the session off. Thanks.
Thank you. Good morning, everybody. So yeah, I get to kick off the first session of Hot Chips 28. My name is Samir Nanavati. I work at Qualcomm. The session today is on HPC and GPUs. And this field continues. They have always been a strong presence as Hot Chips. This field continues to innovate, deliver new applications with increasing complex workloads. So I think today you'll see a glimpse of that again. We have 3 exciting talks today. Stuff on the latest GPU architectures from ARM and Nvidia, as well as an update on the ARM v8 vector architecture. So a couple logistics. The talks will be for about 25 minutes. We'll allow for 5 minutes of Q&A. There's mics for folks to ask questions. When you come to the mic, please state your name and affiliation before asking the questions. And hopefully we can get all your questions answered. Of course, the speakers will be here later during lunch or breaks to answer questions. Okay, without further ado, I will introduce our first speaker, Jem Davies from ARM. So Jem is a fellow and a vice president at ARM. In addition to setting the technical roadmaps for ARM's vision, graphics, display, video products, Jem is also responsible for technical investigations into the acquisitions that ARM does. Most recently, the acquisition of Apical, which led to the formation of their image and vision division. Before that, Jem was also on the ARM CPU Architecture Review Board. He lives in Cambridge, continues to live there after he graduated from the University of Cambridge. He's had his own business for 18 years, and in the last 13 years, he's been at ARM. So my pleasure to kick off Hot Chips and introduce Jem Davies.
Thank you very much. Thanks, everybody. So yes, I'm going to talk today about the first GPU in our new architecture. Yeah, my background is basically looking at technology directions for most of our products that affect pixels one way or another. But first, something of an introduction. Everybody knows ARM. Everybody thinks they know what we do. We don't make chips. So unlike many of the presentations you will see here, I'm not going to be talking about speeds and feeds. I'm not going to talk about frequencies and throughputs. What we do is we sell soft IP, and we then give that to our partners, and they then do a whole bunch of stuff with it. Some people will produce very high-frequency, high-performance implementations on bleeding-edge processes. Some people will do slower ones on more commodity processes. They all have their own businesses to run. They have different requirements. So I'm not going to talk so much about that sort of thing because it's actually very difficult to predict what different partners will achieve. What I'm going to do is talk about our new GPU architecture and our new GPU. There is one marketing slide in this presentation, and before the engineers in the room switch off, I'd just like to explain why I've put this in the deck. It's not to crow, it's because this is actually a problem definition statement. So you don't get to ship 750 million GPUs a year unless you understand the way in which our partners are taking the IP we give to them, and they produce completely different designs. Sometimes they'll go into devices we have no knowledge of or we were completely not expecting. So we have to hit a number of scalability requirements, and we have to hit a number of different segments. Sometimes we will license a GPU to a partner who will then produce multiple different SoCs targeted at completely different market segments. And sometimes the different customers will have completely different performance requirements. So some elements of scalability, both in terms of the actual GPU design itself to address different performance points in different markets, but also the architecture needs to have a certain amount of scalability and flexibility in it in order that individual GPUs within that architecture can hit specific device points. For those of you, and I'm sure there won't be hardly any here, without an encyclopedic knowledge of Norse mythology, I'll just say that the word Bifrost, which is the name we give to our architecture, refers to the rainbow-colored burning bridge between the land of men and the land of gods. See, you all knew that. We have two other architectures, Midgard, which was our first architecture that had unified shader cores, and the oldest architecture, Utgard, where we had the very successful Mali 400 GPU, which sold over 1 billion units. And that one was very much cut down specifically to address OpenGL ES 2 with the requirements there for precision and so on. So, Bifrost itself, what have we tried to achieve? I talked about scalability. We've increased the scalability from 1 to 32 cores. So that's 1 to 32 pixels, output pixels per clock, fully textured and output to main memory. We've completely redesigned the interior of the shader core, and in that we've introduced a new instruction set, which is both scalar-based and also claused-based. And I'll come on to talk about what clauses are and the way in which we've extracted use out of those in our new architecture. We've introduced a new geometry data flow. After all, a GPU is primarily a data flow device. Vast quantities of data are in and out. And for a lot of our customers, that data flow is a primary requirement to keep it as efficient as possible because data flow equals power. And we also have fine-grained buffer sharing, fully coherent, fully cache coherent between CPU and GPU. So let's look at that in a bit more detail then. Looking at the shader core itself, it looks very much like the Midgard architecture, but scales up further. We have our own internal fabric between the shader cores, and we talk out through our own MMU, out through a number of individual cache slices from L2. Looking at the internals of the shader core itself then, what we have here is the quad creator. So we issue 4 threads simultaneously. They could be representing a quad on the screen, 4 pixels together, but it doesn't have to be for compute and so on. Those are issued by the quad manager and issued to the execution engines. In Mali G71, there are 3 of those execution engines per shader core, but that number is not architecturally set, and different GPUs can have different numbers of execution engines themselves. The quad state, the actual state, the register values and so on of the threads themselves is passed with it through each execution engine to keep down the amount of traffic that's going backwards and forwards for each state. There are lots of vectors, obviously, in graphics workloads. The Midgard GPU used a SIMD vectorization approach. We had 128-bit wide vectors, and most of the data then obviously fills the entire width of the arithmetic unit. But in fact, filling all of those 4 lanes simultaneously can be hard to achieve, and VEC3 workloads are actually quite common, and so you can see that if you put a VEC3 down this, you will actually have one of the lanes idle all the time. We've taken quite a lot of strides in compiler vectorization to extract vectorization when there was none inherent in the actual source code itself. But this is hard, it's certainly not perfect, and there are times when you just can't do it. So in the sense that we have a bunch of bricks here that we're trying to put together to assemble those vectors, sometimes you just can't do it. So is there another way we can do this? Well, yes, we can play with PowerPoint and do funny things like that and look at it the other way around. It's always easier to break larger operations down into smaller ones. And so in Bifrost, what we've done is we've broken the problem down the other way. We execute the 4 threads in a quad in lockstep, 1 element at a time. And if you look at a VEC3 operation going down the pipelines like this, you can see that we've now used only 3 cycles, not the 4. And we can eliminate this idle cycle and use it for something else. It also makes the compiler guy's job quite a lot simpler. It's always making shaders faster to compile and more likely to be optimal. You can always put scalars together and to make vectors if you want to. You can always break vectors down into scalars. It's harder to put scalars together to make vectors. Looking at the internals of the execution engine then in more detail, it's a much simpler design than we've had before in Bifrost. There's a 32-bit FMA unit and a 32-bit add and special function unit. The FMA unit is implementing fuse, multiply, add, and the related sort of multiply instructions. The add unit does simpler arithmetic instructions and also special functions, as I'll talk about. And we have a single instruction word, or tuple, as we call it, which directly controls both of those functional units. It's effectively containing sub-instructions for both of the FMA and the add units. The special function unit is considerably smaller than we had in Midgard. It's tailored much more after a very detailed analysis of the real-world shader code that we have access to. We now have a huge corpus of code whose requirements we have analyzed. And what we've done is we've implemented a special function unit with some basic operations we can use to construct the built-in function libraries that will either be used by a compiler inlining code or where that built-in function library is an explicitly part of one of the compute languages we support, such as OpenCL or something like that. We now therefore spend less area accelerating these things, and other more complicated transcendentals can be constructed out of instruction sequences and that only occur rarely. The implementation is full IEEE 754/2008 compliant, of course, as now modern GPUs have to support the compute requirements for the different compute languages such as OpenCL, which has now taken considerable steps forward in defining arithmetic models and memory models and so on. We still retain some support for smaller width data types, and indeed these are, particularly with the advent of machine learning code and computer vision code, these are becoming much more important again. With things like vectors of FP16, These are very commonly present in graphics code. Very little graphics code relies on expressing color precision to 32 bits. There's a lot of 16-bit color precision code around there. That's medium P in OpenGLES speak. And so for that sort of operation, it's possible to double the throughput because we can do 2 FP16 operations for every FP32 we can. And the integers, proper integer support is also included right down to 8-bit as well. A lot of swizzling operations present as well. Clearly, swizzling data formats through a bunch of this is extremely important, but I won't go into too much detail about that. Looking now then at the actual ISA itself, let's talk about clauses. So a clause is a group of instructions which executes atomically. There are a number of different words used in architecture to define this group. We've gone with clause. The architectural state is defined before and after a clause execution with limits on what is architecturally visible between the actual instructions contained within a clause. And that allows us a certain amount of freedom to do things like use temporary registers, which I'll talk about, which can be implemented not as real registers, but as bypass paths. So let's look at a bit of code. Perhaps it'll make a bit more sense. So here's a random piece of code in pseudocode. It's not really doing anything particularly threatening. It's just loading a value, doing some arithmetic on it, and storing it back. And in the simple linear form that you see here, then there are data dependencies contained within that code. You see, for example, that the result of the load is immediately used. Traditionally, in processor architectures, we typically have to identify that as a hazard and then stall the thread until the load completes. The register accesses in the arithmetic section are largely serial too, so there are associated hazards with that. And finally, we write the result back to memory. However, what we can do is to split this up. So if we pull out the dependencies and put the load instruction into a completely separate clause, because we don't know how long that instruction is going to take to execute, we pull that out. And we put the rest of the code into a separate clause with an explicit wait at the beginning. We have to test the control flow for that at the start of the clause, but after that we know we're good to go. We can easily transfer control to other quads if we have stuff waiting, which we will. It's a very thread-rich environment. There's always something ready to go. Now, of course, if we didn't use that R0 value until later, we could defer that clause split and test later too, so that more instructions could execute on that same thread. But we can still do quite a bit better than this. If you take that and wait on that, but we can optimize this further by taking it into 3 clauses. The first clause executes the load. The last clause executes the store. And if you look at the way in which we've rewritten this in the intermediate clause, we've introduced temporary registers. And in fact, architecturally then, this piece of code now only uses one of the main register file registers. And register file pressure, both in terms of numbers of reads and writes per cycle, and also in terms of routing, when you're actually building this functionally, physically, is a big issue. So reducing register file pressure is considerably important to us. The temporary registers are only defined to be valid until the execution of the next instruction within the same clause. So again, they're not real registers. In fact, they're implemented as bypass paths, and we get a good power saving as a consequence of that. What we've done is we've reduced there only 2 main register file accesses in those 6 cycles, which is a pretty good improvement, and we found that our register file is now considerably less of a hotspot in terms of implementing the design. Moving on now to data flow. As I said, for a lot of our customers, data flow is particularly important. massive amounts of data being used in graphics and high-performance compute workloads. And that's power. It's power and it's money because, of course, a lot of these are going into very cost-conscious designs, and the specification of the memory system is something that our customers care a great deal about. So if they can actually specify a lower frequency part, then traditionally that will be a big advantage to them. Almost invariably, these GPUs are going into unified memory systems. We're not talking exotic GDDR16 or whatever it is this week. These are typically LPDDR devices, possibly 1 or 2 chips for an SoC. So reducing data flow, extremely important. We still use a hierarchical binning design as we did in Midgard. We progressively reduced the bins on the screen to the smallest possible bin that can contain a triangle, and that's proved to be very successful for us. But what we've done here is we've redesigned the tiler memory structures to use finer-grained allocation, to use less memory, and this has been very effective. One of the particular things we've also done, which is an example of ways in which you might design your processor not to execute perfect code perfectly, but to execute really average code rather well. Because what we do is we eliminate microtriangles. So a triangle that's been created that actually doesn't affect a sample point in the output of a colored pixel, it simply can't affect the output in any way. And what we've done now with the tiler is to eliminate those microtriangles at the beginning stage, thus saving a whole bunch of work later on. While we were doing that, we've moved to something called, for those of you who really aren't GPU experts, you can skip this couple of slides here. But what we have in graphics is, of course, we're presented with a whole bunch of primitives about triangles. We have to read in the indices for those. We have to read in their positions. Then we have to run the position shader to find out where those triangles actually are. There's also a whole bunch of other work associated with it about shading them to find out what color they are. But if we can do the position shading, which we've done by our compiler is now actually taking the one shader that was presented to us by the user and splitting it into 2, runs a position shader initially. Typically, half of the positions result in something that's not visible, so we can discard them. And then for the ones that pass that test, we then have to shade them with varyings to find out what the colors actually are. And this is serious. I mean, for the T-Rex benchmark, which is pretty much standard at the moment, that's a saving of about 20 or 30 megabytes per frame we're talking about. So it all adds up. You know, you have data flows in and out of memory, and if we can halve a number of those, then you can see on the right-hand side the graphs of reductions of read and write bandwidth. Very significant, as you can see. The memory system being used through this is, as I said, a cache coherent one. We have a scalable architecture as well, so different customers will be deciding on different sizes for the level 2 cache, and depending on the number of cores they fit, they'll be fitting more or less level 2 cache segments. They're present as slices, but it's software invisible. It's just present as one big coherent cache. The tiler is also present within this cache domain, so all of this work is taking place within that coherent domain. Moving on then to the new memory system, a bit more detail about the memory system. We have fine-grained buffer sharing between the cores in our GPU itself and between the CPU and the GPU. Talking to the external memory through ACE memory bus and with a modern CPU, which we can now snoop previously, Midgard could snoop into the CPU's caches. Now, from Mali G71 and Bifrost onwards, we have the ability for the CPU to snoop into the GPU's caches as well. And as we move to new workloads in heterogeneous computing, particularly the advent of computer vision, where you might want to run some processes in a very parallel way on a GPU, but some processes in a very serial way on a CPU, we're seeing good use out of this. The cache design now also is being used to effectively to clean up data transfers. We have partial lines being written to support, which actually improves the performance when talking to LPDDR4. We're using it to shape the right traffic. And of course, coming from ARM, this supports trust zone. We're now having people using the GPU to do composition of secure content or to do transformation of secure content like secure video, highly valuable content. And OpenCL2, of course, implements coarse-grained shared virtual memory as the mandatory model, but Mali G71, when used with a coherent CPU and a cache-coherent interconnect like CCI 500, goes one step further. And we can now, as I say, balance the workloads across different types of devices to very significant effect in terms of cutting down on runtime, cutting down on external memory bandwidth, because we now have direct cache-to-cache transfers, and so on. And it makes for a programming model that is actually intelligible by mortals. If you actually have to have cache coherency and cache consistency being maintained by software, you're probably in for trouble. In summary then, we've taken the best bits of our old architecture. I think we've added on a whole bunch of new features that make this very suitable for ARM's target markets. We've redesigned the internals of the shader core itself. We've made a more scalable architecture, which will probably last for some years now. We will be pushing out new GPUs from that architecture, caring about power and efficiency, trying to drive optimally use of the functional units. And the numbers speak for themselves. We're seeing much better higher energy efficiency, much better bandwidth improvement, and also, because of course ultimately somebody's paying for the silicon that use these things, we're seeing better silicon area utilization as well. Thank you very much. Any questions?
Hello, Alex Board, Qualcomm. So for the 8-bit support, so you said for 16-bit you do 2x performance for FP16.
Yes.
What do you do for 8-bit?
For 8-bit, that'll still only be twice.
Thank you.
I haven't really needed to optimize that. That, of course, is an implementation feature of this particular GPU. That's not architecturally defined. If we found the need to do it in a later GPU within this architecture, then we can tune that.
Hey, Jem, it's Kevin Creewell from Turius. Quick question. Because you've got FP16 support as well as int8, have you looked at tuning the application, the GPU for inference in deep learning as well as its graphics function?
Yeah. Sorry, I don't understand the question.
Well, you have FP16 support,
yes,
as well as int8. Those are really useful for deep learning, for neural net.
Yes. I mean, obviously, these algorithms are in considerable flux at the moment, and there's a lot of work being done on reducing the precision needed to do the inference. I think one of the things that's useful is people are now looking at the neural networks as two completely different domains. There's, training is one domain and inference is another. Inference we see as obviously an on-device problem rather than an on-server problem. FP16 certainly working, but also reductions down to integer. Integer workloads working quite well. Google announced their TensorFlow at the Vision Summit, which strongly encourages the use of smaller and smaller precisions, down to, a few bits.
So are you looking at those workloads for?
We're certainly looking at it. I mean, we're designing an architecture to have some life here. We don't particularly want to chase an algorithm that's being changed every 3 months. But yeah, obviously, having flexibility of data types is something that's very important.
Hi, Jack at Nvidia. So you described the coherent cache within the GPU domain. You showed the L2 cache.
Yep.
You didn't mention a texture cache. Is there the texturing operate directly at L2, or is there an L1 cache?
Texture cache is backed by the L2, but the texture cache is actually a read-only cache. So there's no need to have that take part directly in coherence.
So it's not coherent?
No, because they're read-only textures.
The read-only, okay.
Yeah, I mean, if you do computationally generated texture, then that will obviously be read through the L2, and that is then, so that is the creation of a dynamically created texture will be cache coherent, and then you read it into a read-only texture cache.
So for compute, which may be doing loads and stores, that's operating only out of the L2?
For compute, generally speaking, that's just worked through the normal load store cache backed by the L2. Compute tends not to make big use of texture caches. The API.
Is there an L1 compute cache that's separate from the texture cache?
There are caches all over the place.
And they're all coherent?
Yes.
All right, thank you.
David Cantor. So you described the data paths as generally being 32-bit wide, but you have support for 8-bit and 16-bit data types. So should I assume that instructions that access and manipulate 8 and 16-bit data types, are those SIMD instructions? Or are your registers actually smaller? For the small vectors, those are present within a vector construct in the instruction, but the instructions in general is looking at scalars of 32 bits. So you're constructing vectors of multiples of 32-bit wide. Right, but if I'm doing FP16,
yeah,
right, that's a short vector, right, a SIMD vector.
Correct.
Of 2 16-bit data types.
Correct.
And similarly, if I was doing int8s, that would be 4 within a single SIMD.
Correct.
Okay, thanks.
All right, I
think that's about it. Thank you very much.
Okay, we're just getting started here. Thanks, Jem, for a wonderful presentation. So the next one is from Nvidia. There's 2 fabulous, in my mind, technical talks in this presentation. One is on the Pascal GPU and one is on NVLink. Let me introduce the speakers. Dr. John Danskin is going to lead it off. He's the Vice President of GPU Architecture at Nvidia. Dr. Danskin has been working on accelerators since 1983 at several companies like Daisy Systems, DEC, Dynamic Pictures, 3DFX, Nvidia. At Nvidia, Dr. Danskin is Chief Architect for the Tesla lineup, including the Kepler family of GPUs and now Pascal. He holds a PhD in computer science from Princeton University. The second speaker is Denis Foley. He's a senior director in NVIDIA's GPU architecture. Denis joined NVIDIA in 2012 and leads the teams responsible for the architectural development of NVLink. Prior to NVIDIA, Denis was a senior fellow at AMD and the lead engineer of AMD's initial APUs. ESL positions as system architect for ATI, Imagion application processors, and at Hewlett-Packard as the implementation lead for a 128 processor SMP system. Denis holds a Bachelor of Engineering degree from University College Cork in Ireland. So without further ado, I'll have John Danskin come up.
Thanks. Okay, hi. I'm going to talk about the GPU part, and Denis is going to talk about the NVLink part. This is the outline. We've got a die, it's big, it's bad. We've got a module, it's small, it's bad. I'm going to talk about the like how you build one of these things without it all falling apart on the floor. Some features, performance, and then Denis will talk about our new interconnect. One thing is, so this is a product. It's launched. There's a really awesome white paper. I'm going to talk around what was in the white paper so that this is, as much as possible, all new information. If you feel like I'm talking around some of the core information, you should go look at the white paper. I didn't want to repeat. So here's a die picture. I wasn't allowed to label this, but it's 610 square millimeters, which is bigger than they keep getting bigger, and I think partly this has to do with Moore's Law, and partly has to do with the people's interest in just getting a lot of performance out of GPUs. We have 4 stacks of HBM high bandwidth memory. You can see the controllers at the top and the bottom. We have our NVLinks on the left. There are 30 SMs. I couldn't label them, but I see 30 green blobs. 2 of them are for spares. We have 4 megabytes of L2 cache. So that's a teeny tiny little cache. It's because I have around 30 megabytes of register file. And the cache is really just it's a streaming thing. It's for read-return buffers. It's for so we can do page sorting, just to get stuff in and out. As I said, we have these 4 NVLinks, 16X, PCIe Gen 3. This is the module where pretty exciting module. It's you can see there's the chip in the middle. There's a GP100, the 4 HBMs. You've got and off to the sides, all that stuff is power supply. It's 300 watts, so over 300 amps. You could start your car. It's less than half of the area of a PCIe card, and that's really because the memories are all in the same place. And this will allow us to build much smaller, physically smaller HPC systems. And it supports this, if you look at the bottom there, these connectors, obviously a lot of pins. It supports our NVLink interconnect, and we don't have to run the memory interface off of this chip. So it works. And it's 300 watts. See the power envelopes climbing. So I wanted to talk a little bit about what happens when you design for HBM, this HBM memory. It has to have very short wires on the order of a millimeter or 2, which is okay up to a point, but this is how big of a memory system you can build, right? We sort of run out of package size. Everything has to be next to each other. Now, luckily, they're stacked, so we can get 16 gigabytes in this card, in these systems that we're selling, and theoretically, you could go to 32, which is, by far and away the biggest memory system we've been able to put on a GPU. So that's very exciting. With these, only 4 memory interfaces, you sort of think, oh my goodness, they're going to have huge memory atoms. So actually, we have 8 memory channels, and it's actually quite challenging to put 8 memory channels with GDDR5. So this is actually, it's not a step up, but our memory atoms are of comparable size, because this is wide and slow, where GDDR5 is incredibly fast and narrow, and the memory atoms end up about the same. We have 32 L2 slices So that's 4 per memory controller, and that matches the bandwidth onto our 3 terabyte per second internal bus. So you can see if we have a 3 terabyte per second internal bus, we are actually getting L2 hits in our tiny cache. So it is making a huge difference. It's 4 times as fast as the actual memory system. One thing, this HBM is so incredibly fast, but it's actually, if you look back far enough and you sort of plot out some exponential lines, it's not that amazing in terms of Moore's law. What's really happened is we sort of have been flatlining on GDDR5 for a long time, and then we get this giant jump. It's 3 times as efficient for power. We're only using 5 picojoules per bit. So it's 3 times as efficient as GDDR5. And people who compare to SDDR will say, wow, it's way more efficient. So 3 for us. But just tracking Moore's law, which means we have to do something else really soon now. Even better. So how do we do this? How do we, well, first, what do these look like? It's kind of cool. On the right, you can see our GPU. On top, it looks incredibly thick. On the left, we have the HBM memory. So there are 4 memory stacks, 4 memory die on top. The top memory die of the 4 is really thick compared to the other ones, or the other ones are incredibly thin. For a size guideline, that big black stripe is 1.2 millimeters thick. So those memories are fairly, thin, if that's a millimeter. The top one is so thick so that you could put 4 more stacks on top. You could thin that and put more stacks on top and have an 8 high stack in the exact same form factor. So that's an option that would bring us to 32 gigabytes per GPU. Those memories are on top of a base die, so you have 5 pieces per stack. As I said, there are 4 of them, 4 high today. The DRAM and the GPU are on a silicon interposer. So there's a thin line going under the GPU to the memories. And that's a single layer silicon connectors, very high quality signaling between the memories and the GPUs. So this is a single, all silicon assembly, teeny tiny little micro bumps. And then this thing that looks like a board is really just a package. And there's a board under the package. And it's for a die, it's a pretty big package, unless you're one of these very cool FPGA vendors. So 4096-bit wide interface, that's 1,000 per die or per stack. That's and 500 per memory channel. 720 gigabyte per second DRAM bandwidth. There's going to be upside on that, but that's still 3 times as fast as our previous HPC product. As I said, 3 times the bandwidth at the same power. And the density, the physical density is 4 to 8 times. They're stacked. They don't have packages. It's incredibly dense. We can make incredibly dense modules, even compared to a CPU with all those big DIMMs next to it. So how do you make this thing? You have a die. You've got the 4 stacks. The stacks have 5 die. So there are like 21 pieces of silicon. How do you assemble this and have it, work? So the die, the GPU die is known good before we assemble it. The stacks are known good before you assemble it. So you actually, the micro bumps are too small for testing machines. So you can't possibly test them. So we use magic. The silicon interposer, which is the second layer down, is visually inspected. It's not tested. It's very, compared to the silicon, with the 29 layers it's not layers, but steps. It's a very simple object. So it basically just always works. And then at the bottom of this picture, you're seeing the package. So with these huge those are micro bumps inside the package. So what do we do about warpage? You're assembling this thing, and it's like when you were assembling like a little model airplane, and everything kind of warps when you put it down, and it ping, and it's stuck to your fingers. So why isn't that happening? So we put the chips on a thick wafer. So the thick wafer is not flexy when we're assembling it. Now we've got all this stuff on this thick wafer, the interposer, and then they thin the wafer. So now it's paper thin. And then it goes on the substrate. And the substrate's, like 5 layers of stuff, and then there's 2 layers with the thick thing, and then 5 more layers all glued together. And that's a low thermal expansion core. And even though it's, a whole millimeter thick, it still could be flexy, so there's a band of metal around the outside. Sometimes people put a cap, but that would interfere with the thermals. And like I said, this is 300 watts. So we added some features. I have FP16 at twice the FP32 rate. This chip is 5 double precision teraflops, 10 single precision teraflops, 20 half precision teraflops. We did this for deep learning. It's awesome. Another thing you get from FP16, it's not just the math. You can store this stuff at half the size without doing a bunch of conversion instructions, so you get twice the bandwidth because it's half the size, and you get twice the capacity on your in your memory subsystem. We have FP16 atomics to the memory system so that we can do adds and mins and maxes and all kinds of other cooperative stuff without locking. We had those for FP32 forever, and we just added them also for FP64, which is going to be really great for our HPC customers. More bandwidth per flop, a little bit less than that. Instruction preemption. So we can now, you can interrupt the chip, you can stop, you can look at what was in it, and then we can start it going again on your same program without running it again. All the CPU guys are like, wow, we did that in 1967. Okay, well, we got it. It's there. We have page fault stall. Before we had page fault stall, we had page fault crash. Yes, that was good for protection. With page fault stall, we can stop, you can twiddle the page table, shoot down the TLB entries, and keep going. And this is critical for being able to do page migration and for CPU, GPU interactions and ability to use library calls. And we have 49-bit virtual addresses now, which is enough to play with CPUs. We used to just use virtual memory inside the GPU. Now we can play with CPUs necessary. So this is the automatic page migration. What we had to do before, on the left, before is like today, when you malloc memory, we have to have it in a managed pool. And then when you run a CUDA program, you have to make sure that the memory is loaded into the GPU before you can use it. And then after the GPU is known not to be running, then CPUs can use it and they'll just fault it back into the CPU memory and it's fine. So you do get automatic page migration, but only with managed pointers. So if you make a library call, that library is sort of thinking, is this a managed pointer or an unmanaged pointer? Because if it might be an unmanaged pointer, then it can't call CUDA. So on the right, we have the new improved Pascal memory subsystem working with operating system support. And the big thing is because we can really page fault or page fault stall in the GPU, we can just use normal pointers. And so this is actually huge for, normal pointers shared between CPU and GPU. And nobody has to know about it. Nobody has to think, where did this pointer come from? And 55 seconds to talk about performance. This is a little slightly confusing. Okay, on the left at the top, it says 2x K80s, and we're going to compare 2x K80s to either an M40 for AlexNet, which is deep learning, So 2x K80s, 1 K80 is 2 Kepler GPUs. So 2x K80 is 4 Kepler GPUs, but M40 for deep learning is 1 GM200. GM200 is a Maxwell chip. It's got 30 SMs, the same as GP100. It's really fast compared to anything you could get now. On AlexNet, 2 GP100s is more than 7 times faster than M40. So this thing completely blows away what we had before, which is what we had before is already what everybody uses for deep learning. Now, for all these HPC applications, you've got the gray line, which is 2 K80s, which is 4 Kepler chips, compared to 2x, 4x, and 8x P100. Ooh. And so what you see is just that if the lines were the same, we'd be twice as fast next to each other. And what we're getting is that we're about 3 times as fast most of the time, and we get linear scaling, and that's because of NVLink, and Denis is up and 30 seconds late. Sorry, Denis.
Thank you, John. This is a great setup slide. I'm glad that John left it here for me. Jem from ARM earlier on was talking about how the programming, ease of programming the machine is key. And so we believe that in the GPUs as well. John spent, I think, 5 of his slides talking about HBM and how important HBM is to us. For graphics guys, bandwidth is huge. What's nice about this is that we're looking at some incredible scaling in these predictions that John left up on the screen. And this whole thing about how do we actually scale up a machine, how do we actually make it so that it's easy to program, and how do we actually maximize the bandwidth, not just to the local memory, but between peers and between the GPU and the CPU, is what NVLink is all about. So I'm going to walk you through that. At its core, NVLink is going to work from the inside out, sort of, the wires out, right, and just sort of build up a picture and show you at the end how we actually tie it all together. So at its heart, what we have is 8 differential signals in each direction that make up a single link. So that's a by 8 building block. And running those links at 20 gigabits per second, giving me a total of 40 gigabytes per second of bidirectional bandwidth on one NVLink. The Pascal chip itself supports 4 of those links. So we've got 160 gigabytes per second of bidirectional bandwidth that's available for GPU to CPU communication or GPU to GPU communication. On the physicals, we've got an embedded clock, so we have a clock recovery circuit at the receive end. It's 80 ohm terminated, which is kind of a deviation from the 100 ohm norm for high-speed signaling, but we think that people are actually heading down towards the 85 number. It's DC coupled, and this is more of a statement in terms of making the PHYs easier to design and to actually get rid of external decoupling caps so we don't have those speed bumps for the high-speed signals. We've got a pretty robust error rate, so 1 bit error in every 10 to the 12 bits transmitted. And we almost thought that might be enough to actually sort of let us go without a correction or recovery scheme, but we actually do have a CRC checking scheme as well, and I'll get into that. One of the interesting things is that we're allowing for a 22 dB insertion loss in the channel, and that gives us about a 15-inch reach in some sort of a reasonable board material. And that's key as we look sort of like for placing GPUs relative to other GPUs. When we started this, we were kind of designing a little postage stamp areas. We only had like a 7-inch reach. And the 15-inch reach that we actually pushed it up to actually allows us to do a lot more with what systems we can build. And then we support all the motherhood and apple pie stuff on the links like polarity, inversion, and lane reversal. So if we step up a little bit sort of in terms of what the protocol is, the NVLink itself is a packetized protocol, variable length packets made up of 128-bit flits. CRC protected as I said, and I'll get back to that later on. And then we support up to a 256-byte transfer, and we are 94% efficient with those 256-byte transfers. Obviously, your mileage will vary depending on what sort of operations you're trying to do, reads, writes, whether the links are busy in both directions, and I have a slide to that as well. So one of the things that differentiates us from other interconnect standards is that we can take these individual NVLinks that we have, the by 8 building blocks, and if we have 4 separate targets that we want to actually address, we can have one link going out to each of the targets. If we have a single target that we want to address, we can have a single ganged link, we would call it, so that we have 4 lanes or 4 of these NVLinks that will talk to the other endpoint. And then what we'll do is, we're using some sort of hashing function on the address, we'll spray traffic over the links to get sort of very robust bandwidth on that sort of single interconnect between 2 chips. To address the ease of programming piece of this, what we can do is the GPU can now do full load store directly inline, sort of load store or atomic operation to other GPUs. And to the CPUs, we don't actually support atomic operations to the CPUs yet, but we can actually do load and store to CPU memory directly. So that makes it a lot easier for the programmer to actually sort of figure out how to use this. Okay, so let's look a little bit more at the packet. It's a very length packet, as I said. It's 128-bit FLIT. The header has got CRC information. It's got header information that's actually to do with the transaction that we're trying to do, whether it's a read or write or atomic operation. And then it's got a DL header section as well. The DL header is more of a housekeeping type header. It's got stuff like sequence IDs, acknowledges, and so on for just DL, data link layer functionality, just to make sure we get the packet from A to B correctly. We have an address extension FLIT, which is used for information that doesn't have to be, we don't want to actually have to resend with every command that we have across there. So for instance, upper address bits, which are invariant, we'll send them across once, inserting the address extension FLIT, and then for subsequent operations where they're not changing for that context, we'll just leave it alone and just actually save sending that FLIT. For shorter size read operations, we support the insertion of a byte-enable FLIT. And again, this is an optional FLIT in the protocol. And then we've got some number of data FLITs from 0 to 16 data FLITs, each of them carrying 16 bytes of information. All right, so sample read, and this is pretty simple. Basically, the requester sends out its request. In this case here, it's a 64-byte read request. We've got CRC on it. We got the DL header. The TL header information in this case here is, that's the command. Hits the target responds with CRC, read response, TL header, again the DL header stuff, and then the data payload associated with that. All right, so CRC. So we got 25-bit CRC on each of the packets that we transfer. So whether it's a minimum length, single FLIT packet, or whether it's sort of like the longest packet we support, which is 18 FLITs. The 25 bits allows us to support up to, or to detect up to 5 bits, 5 random bits in error in the packet. Or we can actually sort of figure that we've gotten up to a 25-bit burst in any one of the lanes on the link. The packet header, the TL header, contains the packet length. And so when we want to discover as quickly as possible what size packet we're looking for. So what we do is we actually have the CRC is calculated over the current header and the previous payload. And that says to us that we can have this, we can check out the previous data payload as fast as possible by having the CRC here. But by having the CRC in line with the next command, if you like, we end up having immediate protection on the header information for the current request. So that's just seemed like a pretty neat way to do it. We do have, as I say, this 25-bit CRC that's used. When we actually detect that we have a packet in error, where we get a CRC error, we actually do not acknowledge that packet. So we use a positive acknowledge on every CRC that we get that comes in correctly. And then in the absence of an acknowledge, we're actually going to get a timeout on the sending side. That data will have been squirreled away in a replay buffer, and the replay sequence will be initiated back to the last known good packet that was transferred. So we keep everything on the transmit side until we're certain it's actually been received well. If it hasn't been, then we replay it and come back in line. Okay, so from efficiency, do the math. The unidirectional efficiency is pretty easy. It's, in this case here with a 256-byte transfer, I've got 1 header cycle of overhead, so I'm at a 95% efficiency, and if you just follow this curve down, it's just very simply how much data am I transferring for that 1 header. When I go bidirectional, I have to account for the fact that I've got requests and responses going in both directions. So there may not actually be an opportunity for me to put in a data packet at one particular time. So the bidirectional efficiency is somewhat lower. Okay, so what are we doing? What are we building with this? So this is our DGX1 system. DGX1 has got a fully connected quad on 2 faces of an 8-pack. And then the ends of the 8-pack are actually connected to each other here. So everything is connected up so that no GPU is more than 1 hop away from any other GPU. We get a pretty robust 640 gigabytes per second of NVLink bidirectional bandwidth between the peers. And again, I have full atomics to peer GPUs. And then, obviously, because we want to move a lot of data around, we end up supporting these high-speed copy engines, the high-speed DMA engines at the GPU, which can actually fully soak the NVLink bandwidth available to us. And my teleprompter is getting angry just in time. So we also have NVLink connections to CPUs. In particular, we have a partnership with IBM at the moment where we have an NVLink connection to the Power 8 processor. The system that's represented here is not meant to be representative of any system that we may be building. But in this case here, what I have the opportunity to do is now the GPUs can actually have that very high bandwidth access to system memory as well as the high bandwidth access to peers. And that'll wrap it up for me.
We have time for 1 or 2 questions.
Hi, Alex Burke, welcome again. Question about your atomics. So is it read, modify, write atomics, or you support C11 memory model by any chance, or what exactly for your memory model when you talk to a CPU?
With Pascal talking to the CPU, you're, in effect, yeah, I mean, it supports the C11 memory model, but you're in effect handing off back and forth. It's not a fine-grained handoff. You're page faulting memory back and forth. So the cooperation is really between threads on the CPU on the GPU using the atomics. And that's, yeah, it matches in a C11 atomic thing. I mean, they're atomic, right? What else could I say? It works.
So it's really between GPUs, right? And
yeah, the atomic instructions are only inside the GPU. I mean, CPUs don't have FP 64, 32, 16 FP atomics, right?
So if CPU is more fuzzy, then how do you talk to CPU then?
Pages get passed back and forth.
So you have to shoot down your page in order to get an
you don't see it as a programmer, but it happens. And so the handoff, CPUs and GPUs do not run at the same time on the same memory on Pascal.
Got it. Thank you.
Peter Shu. I'm wondering if you could comment on the sort of business intention of NVLink, or whether from other vendors trying to interface to it, should they think of this sort of more like QPI or more like Ethernet?
We are willing to talk to other people to license NVLink to them. I think our partnership with IBM is evidence of that. It is an Nvidia proprietary standard rather than an open standard, but we are talking to people, talking to partners in terms of enabling them to talk NVLink.
Bill Rash at Intel. What kind of latency are you seeing on NVLink for reads and writes?
The current number for NVLink, the adder for NVLink, is probably in the order of 50 nanoseconds a direction.
Meaning 100 nanoseconds total? Then?
Round trip, yeah.
Yeah, okay, thank you.
We have 100,000 threads running on a Pascal, so we're pretty latency tolerant.
Okay. Thanks, guys.
Thank you.
Okay, the next presentation is by Nigel Stephens and Toshio Yoshida from Fujitsu. So let me introduce the speakers. Nigel Stephens is the lead ARM v8A instruction set architect and an ARM fellow. He joined ARM 8 years ago to contribute to the design of its new 64-bit architecture, having variously been a system programmer, compiler developer, and architect on RISC ever since he worked on the design of the first ever MIPS R2000 Unix workstation back in 1987. Nigel wants to ask a question. Does anyone remember the Whitechapel Computer Works? Okay, Nigel, we have at least one person raising their hand. I'll also introduce the second speaker, Toshio Yoshida is a director of professional development division at Fujitsu and the lead architect for Fujitsu's HPC processor. He has 17 years experience in the development of the SPARC 64 microprocessors for Unix and HPC, including the K computer. He has an MX in physics from the University of Tokyo. So welcome, Nigel.
Great, thank you, Samir. So I'm really pleased to be here today to make the first public presentation of ARM's next generation vector architecture for high-performance compute. So before we start getting stuck into the technical details, a little bit of historical background. The ARM V7 architecture introduced the advanced SIMD, or ARM Neon instruction set, almost 12 years ago to accelerate DSP and media processing running on the main application processor. Now, a few years ago, ARM V8 also included the Neon instructions in its new 64-bit execution state, known as ARch64. And this added some evolutionary improvements to Neon, which made it a much better target for compiler vectorization for general-purpose compute. However, following ARM V8, a number of ARM's partners have asked us to go even further than we went with Neon and provide an architecture which allows vectorizing compilers to extract even more fine-grained parallelism on the main processor by adding such well-understood, well-known features as gather load and scatter store, per-lane predication, and, of course, longer or wider vectors than available on Neon. But therein is the challenge. For a new vector architecture defined in 2016, what should that vector length be? As Jem Davies talked about earlier, the ARM architecture covers a range of different implementations, from very small, high-efficiency designs to very large, high-performance designs. And each of these need to make different trade-offs in their design, and the vector length is a big part of that. So what's the right value? And that's the tricky problem. What are we going to do? So I would like to introduce the ARM V8 scalable vector extension. ARM's conclusion was that there is no preferred vector length for the architecture. Instead, SVE makes the vector length a hardware choice for the CPU designer, allowing it to be anywhere between 128 and 2048 bits per vector in increments of 128 bits. It also introduces a vector length agnostic programming model, which allows the software to be written such that it can adapt to the available vector length of the hardware. This is really important because it allows you to write your code for SVE once, either compile it or hand code it if need be, and then run it anywhere on any SVE implementation now on different implementation nodes or into the future as the vector length increases. But what SVE is not is an extension of advanced SIMD. It's a completely new set of A64, that's the 64-bit instruction set, A64 instruction encodings. And its focus is very specifically vectorization of scientific workloads for the HPC market and not DSP and media processing as provided by Neon. However, it's all very well having these huge vectors, that's great, but Amdahl's law tells us that a task's potential speedup is really governed not by the size of the vectors, but actually the size of its unvectorizable parts. And compilers are all too often unable to vectorize the important loops in a program, which leaves that big wide vector unit underutilized and fails to deliver the performance that people would expect. So SVE also begins to address some of the traditional barriers to compiler auto-vectorization. So what does SVE add to the AArch64 architecture? First of all, it adds 32 scalable vector registers, Z0 to Z31, which extend the Neon 128-bit registers up to a maximum of 2048 bits in length. It introduces also a set of 16 scalable predicate registers. These have between 16 and 256 bits per predicate register, i.e. 1/8 of the vector length. P0 to 7 is used to control the normal vector load, store, and arithmetic operations, permutes and such like. P8 to 15 provides an additional 8 predicate registers for predicate storage and for predicate manipulation. And then finally, there's a dedicated FFR, or first fault register, of which I'll speak more later. And then finally, added to the architectural state is a set of system control registers to control the extension and to allow software to constrain the vector length at each privilege level. So how are the SVE vector and predicate registers organized? So our vector registers can hold packed or unpacked elements of 8, 16, 32, or 64 bits. The predicate registers are organized instead as if they were byte enables. So they have 1, 2, 4, or 8 bits per predicate element, corresponding to the length of the vector element. But only, and this is quite important, only bit 0 of that predicate element is what indicates whether the predicate, whether that lane of the vector is active or not. And the other bits in the predicate element are ignored. So the final diagram up here shows an interesting property of this organization, which is that a single predicate register can control a mix of different vector element sizes. In this particular case on this diagram, it's showing an unpacked 32-bit vector together with and how that can also, that same predicate can also be used to control a vector of 64-bit packed elements. Now, this is really important when you're vectorizing code which contains a mix of different element sizes. So, predication is a critical part of SVE, and in particular, predicates are used to drive loop control flow decisions. And this is very important for efficient generation of vector length agnostic code, as we'll see later. So most predicate generating instructions in SVE can set the ARM N, Z, C, and also V condition flags based on the result of the value of the predicate that they're generating, as shown in this table here. The first active element, no elements active, and last element active. Now, the advantage of this, overloading the NZCV condition flags, is that we can just reuse the existing A64 conditional instructions, conditional branch, conditional select, and so on. All that happens is, as in this table on the right, we rename the condition codes and obviously they have a different interpretation when used in an SVE context. But the instruction, we don't have to invent a set of new conditional branch instructions. Now, how did we fit all of this new functionality, gather, scatter, loads, predication, and so on, into an existing fixed-length 32-bit instruction set? So we targeted only the A64 instruction set, not the old AArch32 ARMv7 instruction set. This diagram here shows effectively the current allocation and usage of A64, and you can see on here that there's there is exactly 25% of the instruction set unused and unallocated. So our goal for SVE was to fit all of the functionality into one quarter of that remaining space. In other words, half the space occupied by the existing advanced SIMD and Neon. 28-bit encoding, a 16th of the total instruction set space. And for a rich instruction set, as I've just described, this was quite a challenge. So let's zoom in quickly and have a look at how that was done. So this is the SVE encoding in 28 bits. It's a load store architecture. It has many different addressing modes, gather, scatter, contiguous accesses, and so on, which means that load stores occupy half of the total encoding of SVE. So this needed some quite careful design, and could have quite easily gone beyond that, of the addressing modes and such like. But the good news is, we don't actually need to encode the vector length in our instructions. As we've talked about, it's a variable length a vector architecture, and the vector length is handled dynamically through predication. So that's good news. We also didn't need to include all of the neon saturating fixed point arithmetic that's used in media codecs and such like. We're only dealing with basic integer floating point arithmetic as used in higher level languages for HPC. And we had to be a bit creative. So adding predicated vector operations can quickly use up a lot of space. So we had to be quite clever here. But we met our goal. We fitted the whole of SVE into 28 bits of encoding with nearly a quarter of it still free for future expansion. So I mentioned the challenge of fitting in predicated vector operations, and here's why. So a fully constructive operation, in this case an integer add in SVE, with predication would be a very expensive thing to encode. And this is what it might look like if you had such an instruction in SVE. You have 3 vector registers, a destination, and 2 source registers, and they're 5 bits each. You have a controlling predicate register, that's 3 bits. You have a zeroing and merging option for the inactive lanes, that's 1 bit. And then you have a 2-bit element size, 8, 16, 30, or 64 bits. So that adds up to 21 bits already, and that's before we've even thought about the opcode. So clearly, we'd very quickly run out of space in our 28-bit encoding. So the decision we made was to make most SVE arithmetic destructive with merging predication only. That means immediately that we can save 5 bits from a register field and 1 bit from the zero merge select to get us to 15 bits. And also we provided some special instructions to do reversed operations. But sometimes a compiler still needs to generate a fully constructive instruction when it needs to preserve both of the source registers. So how did we deal with that? In SVE, we invented this concept called the move prefix instruction. The move prefix instruction can be placed immediately before a destructive encoding in order to create a 64-bit instruction, effectively, which the hardware can easily recognize, but is not it is not mandatory for it to do so. They can also be treated as separate, completely separate move and add instructions as well. And it will give exactly the same result without requiring any additional architectural state to support that. All that software has to do is make sure that the ZD and PG registers match, or else the result will be unpredictable. So this is a technique which we call software-assisted instruction fusion, which allows us to expand that 28 bits. Now, a variable vector length instruction set also places other new requirements on an ISA. There are things that you can do with a fixed length vector that you can't do with a variable length vector. For example, you can't initialize an index vector or a predicate from a constant in memory because you don't know how long it is. So instead, we have to have new instructions, like here the index and ptrue instructions, which can generate the most common index patterns and predicate patterns. Likewise, a vector loop increment and a vector loop trip count is unknown at compile time. We don't know how many elements we're operating on per iteration. So we have new instructions to increment a loop counter and to compute the predicate for the next iteration of a loop. And then also the stack layout is going to be unknown at compile time. Depends on the size of our vector registers when we spill and fill them to the stack. So we have new instructions which operate on memory using in units of the vector length and not bytes. And so on. So let's put this all together. Don't panic. I'm not going to walk you through this in huge detail. I just wanted to illustrate the point, which is that here is a simple DAXP matrix multiply kernel, unit stride. If you're interested, there is an unrolled version in the backup slides, which you can look at later. But the important thing to notice here is that there is no overhead in instruction count for the SVE vectorized version of this loop relative to the one on the left, the scalar code. All that happens is the red instructions here on this slide, which are the scalar loop management instructions, are replaced by the green SVE loop management instructions on the right. And this code is naturally vector length agnostic, no extra work required. And this is great because it allows a compiler to opportunistically vectorize loops when it doesn't know the trip count in advance, and it might otherwise decide it was too expensive to vectorize it. So another use of predicates, I said predicates are important, in SVE is to permit speculative vectorization. This uses a concept called vector partitioning, which splits a vector into shorter segments representing consecutive scalar loop iterations, which can be safely processed in response to dynamic conditions in the code. For example, an uncounted loop, such as a while loop or a loop with a break condition, can be split into separate partitions where the partition prior to a data-dependent loop exit can be performed, whereas the subsequent partitions do not affect the program state. And a speculative vector load. Here, the partition prior to a speculative load fault can be processed as normal. The partition following a speculative load fault must be suppressed until a loop exit condition has been resolved. And then finally, a partition could also be defined by the current vector length and the remaining scalar iteration count of the loop. In other words, vector length agnosticism. So vector length agnosticism is a special case of vector partitioning. Now, again, don't worry, we're not going to go through this in detail. There's a lot of detail here showing how the speculative first fault loads work, and I won't go through it now, bedtime reading. The important point is that SVE adds these new instructions, first fault vector load instructions, which allow software to speculatively load elements beyond the current scalar loop iteration, where that current scalar loop iteration is represented by the first active element in a vector. The first active element must succeed, but a fault that occurs beyond that is suppressed, and the dedicated FFR register, which we mentioned before, tells the software which elements were successfully loaded and could be processed safely. Put that together, what we have here is a simple string length strlen function, which uses speculative loads. On the left, we have a simple-minded, very unoptimized scalar implementation, reads a byte at a time and checks for a null byte. On the right, we'll have the SVE version. Now, it does require some extra instructions to manage the software speculation that we're doing here. So, for example, here in blue, we have the set FFR, read FFR instructions to manage the FFR register around the first fault load instruction. We have a new break instruction here, which is used to detect the first null character or first condition of any sort in the string that we're checking, in the returned vector. We have a new increment instruction to increment our pointer, which increments it by the number of characters that we've, or bytes that we've successfully processed in this iteration of the loop. And finally, we have a conditional branch, which tests for the end of string condition. So obviously more overhead here. In reality, you wouldn't write your code like this. It's just to show how it works. But this would be expected to pay off when a string is longer than, say, 8 characters in length. Another operation that we try and accelerate, other hard-to-vectorize loops, which we try and accelerate in SVE, are loops which have loop carrot dependencies. These complex loop carrot dependencies are a major barrier to vectorization, which SVE helps to address. And it does that by allowing us to split such a loop into 2 separate subloops, a scalar loop, followed by a vectorizable loop. Obviously, that's only worthwhile if you can get some benefit from vectorizing, but nonetheless, this shows the principle. In this case, a serial pointer chase is unparallelizable. It must be done as scalar code, but the rest of the loop can be vectorized. SVE does that by introducing a set of instructions. The most important one is pnext. Pnext allows you to iterate serially through the active elements of a partition, selecting each element in turn and operating on that in place within the vector. And also interesting in this loop is the cterm instruction, which can be used to detect either the end of the data condition or the vector is full condition, allowing you to much more efficiently process that scalar loop. But it is just an enabling mechanism. In this particular case, you wouldn't write it like this. You'd just do better to use scalar code. So let's just put this all together and say, what does it give us? So here, we've got some results which show why SVE is a good compiler target for HPC. We have a set of compiled, single-threaded C and C++ HPC workloads. No hand coding here, all compiled code. The results are all relative to Neon, so it's already comparing to vector code, not scalar code. The gray bars show us the delta, the increase in percentage of vector instructions at 128-bit vector length. So it's showing us the additional vectorization that SVE is able to expose. And then the colored lines show us the cycle speed up at 3 different vector lengths for SVE. 128 bits, same as Neon, 256 bits, and 512 bits. And this is key, that it's exactly the same program binary we're running here. We haven't recompiled anything. All we've done is moved the dial on the vector length in our simulator. And where we've achieved significant extra vectorization, that gives us that extra uplift and scaling by vector length. I would point out that this is an architectural model. These are simulated cycle counts for a plausible SIMD out-of-order pipeline. They don't actually represent a real CPU. And there's clearly work to do here. It's early days for SVE compilers. Major code quality issues do still exist, as you can see with some of the red workloads here, which do not scale well. But it shows a lot of potential. So the next steps are that SVE is available. It's been designed for our partners wishing to enter the HPC market with ARMv8A, and we have lead partners implementing it. It's real. And one of these has been announced already. Almost immediately, we'll start sharing our patches and engaging with the open source communities, standard bodies, and such like, to add support for SVE to various tools and operating systems. And we'll make all of the detailed specifications available later this year or very early next year. So that's it from me, but it's not the end of this talk. You might say this is hot chips, so where's the chip? So at this point, I will hand over to my colleague and friend, Toshio Yoshida from Fujitsu, who will tell you a little bit more about that. Thank you.
Thank you for kind introduction, Nigel. I'm Toshio Yoshida, the lead architect of the Fujitsu's HPC processor. I'm very honored to be here today for the launch of the ARM's new architecture called SVE. I'd like to make an introduction of the Fujitsu's HPC processor for the post-K computer, which conforms to ARMv8A with SVE. Here is a key message of my presentation. Fujitsu, as a lead partner of ARM, has been collaborating with ARM and contributed to the development of the HPC extension called SVE for ARMv8A, which is a cutting-edge ISA optimized for HPC's wide range of HPC real applications. Fujitsu is developing a new HPC processor conforming to ARMv8A with SVE for the post-K computer. This is based on our own microarchitecture as used in our ongoing SPARC64 and our mainframe processor development. I would like to give you a brief overview of post-K processor. It enhances and inherits the superior feature of the K computer Prime HPC FX10 and FX100. To achieve the high performance for a wide range of real applications, many core processor is equipped with a 512-bit wide SIMD. To maximize its performance, Fujitsu is also developing our own HPC compiler for the ARM ISA. This is optimized for our microarchitecture. As you can see in this table, the post-K processor enhances the main functions required for HPC, such as the SIMD widths, 4-operand FMAs, gather and scatter instructions, predicated operations, and mass accelerations. It also supports the hardware barrier and sector cache functions as Fujitsu's unique HPC extensions. For high scalability, this processor uses scalable and integrated TOF interconnect. Assistant core is embedded for handling daemon, IOs, and asynchronous communications. Of course, this processor is optimized for performance per watt. Let me explain about the post-K development at Fujitsu. Fujitsu has 14 years experience in supercomputer, where we have consistently adopted the most appropriate ISA for each project, such as the HPC extensions for SPARC v9 called HPC ACE. Now, Fujitsu chose to adopt the ARMv8A with SVE in order to best position the post-K computer to contribute a wider user base and utilize its assets, such as a software ecosystem to be developed around the ARM architecture. This decision was also a natural result of the close and intense collaboration with ARM on the development of the HPC extensions. The post-K computer will be a massively parallel supercomputer systems based on Fujitsu's ARM-IS-equipped HPC processor, leveraging the Fujitsu's trusted technologies, including the compiler, system software, and file system, to enhance and protect users' application assets. I'm very motivated to make this supercomputer the best in the world, and my team is working tirelessly to make this a reality. Thank you for your attention.
We're running a little late, so we're not going to allow Q&As right here, but both Nigel and Yoshio will be available at the corner here if folks want to come up to them and ask questions.